Today, we are going to uncover an invisible, hidden landscape that exists all around us, and actually even inside of us. It's the invisible terrain of electromagnetism. Now, you obviously can't see it with your eyes, but every single charged particle in the universe interacts with it constantly. So we're going to map out exactly how this unseen space stores energy, directs forces, and, well, fundamentally holds our entire physical world together. To get started, I want you to imagine trying to push the north poles of two really powerful magnets together. You know that feeling, right? You can physically feel that invisible cushion of resistance pushing back at you. Your muscles are doing actual work, you're burning calories, just to force them closer. But where does all that energy actually go? It doesn't just disappear into nowhere. It gets stored directly in the invisible field between them. The exact second you let go, they snap apart, and that stored energy transforms instantly back into motion. This incredibly tactile feeling, pushing against a repulsive force, is literally the perfect way to understand the abstract concept we're tackling today, potential energy. All right, Section 1, Unseen Forces and Potential Energy. Okay, let's dive into this by comparing two distinct forces. We are all intimately familiar with gravitational force, which acts on masses. But if you compare that to the Coulomb force, which acts on electrical charges, what's genuinely fascinating is that these forces are mathematically like siblings. They're both conservative forces, and they both have this inverse square dependence on distance. The main difference, the masses in the gravitational law, are simply swapped out for charges in Coulomb's law. And just like moving a mass in a gravitational field changes its potential energy, moving a charge in an electric field does the exact same thing. Think of shoving a massive boulder up a really steep hill. Obviously, the higher you push it, the more gravitational potential energy you store. Well, in the microscopic world, pushing a tiny charge against a repulsive electric field stores what we call electrostatic potential energy. If you push a positive charge toward another positive charge, you're fighting repulsion. The work you do making that happen, without accelerating the charge, just moving it steadily, gets stored entirely as potential energy. If you suddenly remove your external force, the electric field takes over and the charge goes flying, converting that potential right back into kinetic energy. Moving right along to Section 2, Defining Electrostatic Potential. Real quick, before we get to the math, let's take a brief historical breather. We have to talk about Count Alessandro Volta. He was a brilliant Italian physicist from the late 18th and early 19th centuries. At the time, scientists noticed frog muscles twitching when touched by metals, and they thought it was some mysterious animal electricity. Well, Volta proved them wrong. He showed that electricity was actually generated whenever a wet body was sandwiched between dissimilar metals. This discovery literally led him to develop the very first battery, the voltaic pile. And it's in his honor that we measure this electrical landscape in a unit you definitely know, the volt. So what does this all mean? How do we actually define this volt, or electrostatic potential? Imagine an electric field created by some giant cluster of charges. If we want to measure the terrain of this field, we really don't want our measurement to depend on the size of the test charge we happen to use to probe it. So we divide the work done by the amount of our test charge. Electrostatic potential, denoted by capital V, is quite simply the work done per unit test charge. By doing this, we get a pure value that describes the landscape of the field itself, completely independent of the specific charge we place inside it. Which brings us to Section 3, Potential of a point charge. Let's narrate the ultimate hero's journey for a tiny positive test charge, because only the difference in potential energy truly matters in physics. We have to choose a starting line. We conveniently set our zero potential point way out at infinity. So, Step 1, our test charge starts at infinity. Step 2, we push it inward radially against the repulsive force of a central positive charge. We integrate the force over the distance, fighting literally every inch of the way. Finally, Step 3, all that work we just did becomes the stored potential at our final destination, which is a distance r from the source. Now here is the absolutely crucial takeaway. Electrostatic potential falls off proportionally to distance. Basically, if you double your distance from the charge, the potential drops by half. It's this gradual, steady slope, mathematically mapping out exactly how much work it takes to reach any given point in space around that single charge. Next up, Section 4, the electric dipole landscape. This is where it gets super interesting, especially when we look at the contrast here. An electric dipole is simply a positive and a negative charge separated by a small distance. While a single point charge's potential falls off as 1 over r, a dipole's potential falls off way more rapidly, at 1 over r squared. Why? Because from far away, the positive and negative charges of the dipole effectively start to cancel each other out. The further away you get, the more their opposite potentials blend together, dropping the overall potential to 0 incredibly fast. But wait, there is a totally fascinating twist here. Unlike the perfect spherical symmetry of a single point charge, where the potential is exactly the same as long as you stay at a constant radius, a dipole's invisible landscape has profound directionality. The potential depends not just on how far away you are, but on the angle you're viewing it from. In fact, if you map out the exact middle ground between the two charges, what we call the equatorial plane, the potential drops to exactly zero. The positive and negative forces perfectly balance each other out right there.
All right, Section 5, Mapping Multiple Charges.
Fortunately for us, potential obeys the superposition principle. That just means to find the total potential in a complex system, you just algebraically add up the individual potentials. No complicated vector geometry required, which is a relief. Let's act as detectives for a second. Imagine a positive charge and a smaller negative charge sitting 15 centimeters apart. Because they have different strengths, the point where their potentials perfectly cancel out is definitely not dead in the middle. So where on the line between them is the potential exactly zero? So, if we talk through the math, we basically set the algebraic sum of their potentials to zero. If we look at the position between the charges, the positive and negative potentials perfectly balance out at a distance of 9 centimeters away from the positive charge. But look at the extended line, there's actually a second zero potential valley sitting outside the charges, exactly 45 centimeters away on the weaker negative side. By simply adding the values, we can map out these hidden zero elevation valleys in our electromagnetic terrain. Finally, Section 6, Navigating Equipotential Surfaces. An equipotential surface is precisely what it sounds like. It's a surface in space where every single point has the exact same constant value of potential. Connect this back to that topography analogy we used earlier. If you've ever looked at a hiking map, these are exactly like contour lines. If you hike along a single contour line around a mountain, your elevation never goes up and it never goes down. For a single point charge, these surfaces are perfectly concentric spheres expanding outwards. And this brilliantly illustrates the physical reality of these spaces. There are a few fundamental rules we have to keep in mind here. First, if you walk along the contour, the equipotential surface, you do zero work because you aren't fighting the field at all. Second, the electric field lines are always perfectly perpendicular or normal to this surface. If the field weren't perpendicular, it would mean there was a slope along the surface, which would require work to move across, completely breaking the very definition of the surface. And that leads us to a beautifully simple idea. The strength or magnitude of the electric field is literally just the measure of how steeply the potential changes per unit of distance. If you step off that flat equipotential contour line, you fall straight down the steepest electric field line. The closer together the equipotential surfaces are, just like tightly packed contour lines on a steep cliff, the stronger the electric field is in that exact region. As we wrap up this explainer, I want you to remember Volta and his experiments with the frog muscles. He proved that biology isn't magic. It is governed by these exact same physics. Right now, every single cell in your body is acting as a tiny battery, actively pumping charged ions back and forth to create electrical potentials. This is literally how your brain sends signals, it's how your heart beats. So knowing what you now know about charges, dipoles, and fields, what do you think the incredibly complex, shifting, invisible, equipotential surfaces of your own nervous system look like right at this very second? It is a shocking landscape to imagine, isn't it? Thanks for exploring it with me.